Alright, this is Mr. Gillum, and today we're going to learn how to use the greatest common factor to solve some word problems. Now, some of the problems look kind of long and might be discouraging, but a lot of what's in there is just information. Like, for instance, it says Mr. Ken is making prize bags for a party using two types of items. So what that means is in each bag there will be two different things. He has these things to choose from: soft candies, hard candies, mini pencils, mini pens, chocolate coins, and mini puzzles. Okay, he can choose to make the prize bags up of these things. So even though there's a lot of reading to do here, I mean, all the way to there, all it has said is that he's making prize bags and these are the prizes. All right. Then it says whichever two items he chooses, he wants to put in each bag the same number of the first item and the same number of the second item so that all the items of each type will be used. Okay, and so that one you might have to read twice. It says whichever two items he chooses, he wants to put in each bag the same number of the first item and the same number of the second item so that all the items of each type will be used. So for instance, if he's going to put 2 chocolate coins in one bag, then he also needs to put 2 chocolate coins in every other bag. Or if he's going to put 3 mini puzzles in one bag, he wants there to be 3 mini puzzles in every bag. So he's going to put the same amount of each thing in each bag. All right. So for instance, if Mr. Kent has these things as listed below: 14 chocolate coins and 21 hard candies, 5 mini pencils, 20 mini puzzles, 9 soft candies, and 27 mini pencils, it says what could he make using these things. So if his prizes were 14 chocolate coins and 21 hard candies, and he has to have the same amount of chocolate coins in each prize bag and the same amount of hard candies in each prize bag, but he also has to use all of them up, we know that we have 14 and we have 21, right? But we know that 14 and 21 have a greatest common factor of 7. So he can make 7 prize bags with 2 chocolate coins and 3 hard candies in each one. Okay, so this is a great example of a problem that finding the greatest common factor is beneficial to us, because we know we could have 7 bags, prize bags. Each one of those 7 prize bags would have 2 chocolate coins and 3 hard candies. Okay, now the question asks us, what is the maximum number of bags that he can make with these items? So to answer the question, we would have 7 bags of these things, and we would use up everything in those 7 bags. Okay, so 7. All right, between the 5 mini pencils and 20 mini puzzles. I have 5 pencils and 20 puzzles, and I know that they have a greatest factor of 5. And 5 times 1 is 5. 5 times 4 is 20. And so he can make 5 bags of 1 mini pencil and 4 mini puzzles. Okay. And finally, 9 soft candies and 27 mini pencils. I know they have a greatest factor of 9. And so we could have 9 bags, each bag having 1 soft candy and 3 mini pencils. Okay, so I'm going to go back to this first example in the red here, and I'm going to draw a picture for you so you can kind of get the idea. If I have 14 of the chocolate coins, and I have 21 hard candies. If I try to make these into even groups, it's going to be really hard for me to do with a diagram. So if I say, okay, well, I'm going to take 2 reds, and I'm going to use 3 greens. Okay, so then I would have 3 less greens and 2 reds. 2 less reds, and then I would do it again for my next bag. 2 reds, 3 greens. Okay, so we'd have 1 less row of each one again. And then again, I could have 2 reds and 3 greens. So those will be gone. And you can see that what's going to happen is I'm going to have actually 7 bags, and I'm going to use up everything. So again, I'll have 2 and 3 make those are used up now. And then again, I could do 2 and 3, and those would be used up again. 2 and 3, those will be gone. And finally, 2 and 3. So each red dot represented one of my 14 coins, and I put 2 in each bag, and I've used them all up. And each green dot represented one of my 21 hard candies, and as you can see, I've used all my 21 candies up. So together, here's the first bag, second bag, third bag, fourth bag, fifth bag, sixth bag, and seventh bag. As you can see, I have used up 7 bags right there, and I've used up everything, all 14 chocolate coins and all 21 hard candies without anything left over. All right, so greatest common factor is a little quicker than maybe drawing a diagram. We're trying to figure it out that way. Use that greatest common factor and you can see exactly how much you need to use up everything. Again, another word problem. It says Danny walks a total of 8 miles to and from school each week. Susie rides her bike a total of 28 miles to and from school each week. Now, I know that this is probably a problem that we could solve very quickly another way, but in the directions it says use the greatest common factor in the distributive property to complete the equation and find the total number of miles. Trip and Lindsay, oh, Danny, sorry, that should say Danny and Susie. That's not Trip, that's Danny and Susie have traveled to and from school each week. Well, I can tell you that we know that 8 miles for Danny and 28 miles for Susie is going to give me 36 miles is how far they travel to and from school. So I know that it has to equal 36. Okay, but I want to use a distributive property to what we call factor this. So if I look for the greatest common factor between 8 and 28, just a reminder, you can always use a factor tree to decide what the greatest common factor is for these, and we practice these as well. So 8 would have a 2, 2, and 2. 28 would have a 2, 2, and 7. So they both share a 2 and a 2. 2 times 2 is 4. So I know my greatest common factor is 4. And 4 times 2 would equal 8. And 4 times 7 would equal 28. Alright, so I know that they travel a total of 36 miles. And Danny looks like only goes to school. They look like they only go to school about 4 times a week, and each one of those times it's 2 miles for Danny every day and 7 times for Susie every day. So again, it's just another example of the greatest common factor and where it can be useful. And finally, our last problem says a florist has an order to make flower bouquets. The order calls for the use of 54 roses and 99 carnations. Each bouquet must be the same. If all of our flowers are to be used, there can be at most blank bouquets made from the flowers requested in the order. So this problem is very similar to the first example that we did, where we have to use all of the materials, but we don't have any left over. We don't have any waste. So again, I'm going to use 2 different colors this time. I have 54 roses, and I have 99 carnations. Okay, so altogether I have 54 and 99 flowers. So I need the greatest common factor between those 2 numbers to see how many bouquets I can make evenly and still use up all the flowers. So what I'm going to do is, because 54 and 99 are such big numbers, I'll go ahead and do a factor tree. It's good practice, and we like factor trees. And I can probably do my factor tree a little easier than you. Sorry, a little quicker than you. I know a lot of you think I write a little too fast sometimes. If you need to pause, I know that everyone can do a factor tree well, and go ahead and pause it and get the factor tree down the right way. It looks like my marker stopped working on me. Oop, there it goes. Okay, sorry about that. threes. And so 54 would be 2 times 3 times 3 times 3. And 99 would be 3 times 3 times 11. So I see that they share a 3 and another 3, and I know 3 times 3 is 9, so the greatest common factor would be 9. And I know that 9 times 6 equals 54, and 9 times 11 equals 99. So I would have 9 bouquets with 6 roses in each bouquet and 11 carnations in each bouquet. And I would use up all the flowers, and there would be no leftovers. All right, so that's it for today. Hopefully those 3-word problems make those study island problems a little more clear for you. You have an idea of how to solve those. And that's it for today.